Okay, so question number 4 on the midterm. Let's see. So there's a few given here. So guys, corrosion here is a failure, okay, or a corrosion-induced hole. Let's call that a failure. Okay. In part A, we're given that the probability of having one failure in 5 kilometers is equal to 0.04. And what we want to find is this. What we want to find is the probability of having 2 failures or 2 corrosions in 30 kilometers. Okay. So to find this, okay, if you read this carefully, okay, this is number of occurrences per time frame or space frame. Okay. So it looks like whatever this random variable is, okay, let's call that x, is number of failures in 30 kilometers. So as long as we know what the average number of failures in 30 kilometers is, then x will have a Poisson distribution, where x is Poisson with some lambda, or the average number of failures per 30 kilometers. And I'm just going to put a subscript there, 30, to denote that it's the average number of corrosions per 30 kilometers space frame. So if we know what lambda 30 is, then this probability will simply be e to the power of minus lambda sub 30 times lambda sub 30 to the power of 2, all divided by 2 factorial. The question is, we need to grab or find what lambda 30 is from the given probability here. Now read this question carefully. Okay, this is still the number of occurrences per space frame, in this case distance. Okay, so that in itself also has, or also seems to be, a Poisson distribution. So let's call y number of failures per 5 kilometers. Okay. And obviously lambda 5, let that be the average number of failures per 5 kilometers. And we'll just call lambda the average number of failures per kilometer, or just 1 kilometer. Okay. So the relationship between this would be lambda 5 would simply be equal to 5 lambda. Okay. So from this given probability here, so let me just change color, that right there. If I could rewrite that, that's equal to the probability of y being equal to 1. Okay. And y here has a Poisson distribution. Okay, I should say y has a Poisson distribution with some unknown lambda 5. Okay, and we can solve for that lambda 5 because we are given an equation here. So plug this in into, obviously we're told that that's equal to 4%. Plug y equals to 1 into the Poisson formula. And we have that being equal to 0.04. Okay. Now I can re-express e to the lambda 5 and lambda 5 to the power of 1 in terms of lambda only. Okay. The problem is we can't solve this equation, okay, because we have a lambda 5 in the exponential. So because we can't solve this, nonetheless, I mean obviously using Newton's method, you can solve it using some kind of iterative formula, and I've done that. Now, for the purpose of this course, I doubt that you guys need to know Newton's method and solve for lambda like this. Okay, but nonetheless, I've done it. And before solving it, I've re-expressed lambda 5 in terms of lambda, which is the average number of failures per kilometer. Okay, and solving for this lambda using an iterative approach, I get 0.008341. Now here's the catch. Okay, now here's what's beyond me. Okay. The solution that was given to you by your professor calculates lambda to be 0.04 divided by 5 kilometers, which yields 0.008. This formula here is beyond me. I have no idea how he came to reason this particular number. If you have a good reasoning, let me know. Drop me a line via email. Okay. But as far as I'm concerned, okay, that right there, I don't think there's anything wrong with this reasoning here. So what I'm going to do is I'm going to use this to solve this question. Okay. So continuing here with what we wanted to find in the first place. Okay. E to the minus lambda 30 will be e to the minus 30 times lambda, or the average failures per kilometer, times 30 lambda squared divided by 2 factorial. Okay, sub in this lambda that we've computed in here. Okay, and if you compute this, let's see, what number do I have? I end up getting 0.0244.